Okay, in this lecture we're going to start our Chapter 4 material on differentiation of functions of several variables. And in section 4.1 we'll introduce the idea of a function of more than one variable. So everything that we've been considering in Calculus 1 and 2 in prior courses, we've been working with functions of the form y equals f of x. So these are functions which take some input, a single variable x, and they give some output, some real number assigned to that input. So what we're going to start considering are functions of 2, 3, or more variables. And in this section, we'll introduce these multivariable functions, see what they represent, and learn how to determine what their graphs look like or what their domains would be. So let's start this section by introducing a function of two variables. So a function of two variables is some rule that assigns a unique real number, which we will denote as f of xy, to each ordered pair xy in some set D, which is a subset of the real plane. So the idea is we're taking a point in the xy plane and we're assigning to each point in some subset of the xy plane a unique real number, which is denoted as f of xy. Now the set D that we're taking points from is called the domain of our function f, and the set of all outputs f of xy such that xy is a point in the domain is called the range of our function. So to illustrate the idea, let's say that we're considering some subset of the xy plane. So maybe some plane region shown here. And for points within this region, which would be the domain of our function, I'm going to say some point x, y, we are assigning to that point a unique real number. So on the number line, we have some output, which we would denote as f of xy. Or for other points in our domain, let's say some point maybe AB, we would have a different output, which we would denote as f of AB. In this function, f is the function which is assigning, or it gives us a rule by which we assign real numbers to each of these points in our domain. So let's look at some examples of evaluating a function of two variables at a given point. So here we're asked to evaluate each function at the indicated point. And in part A, we have the function f of xy, which is defined by the square root of x plus y, and we're supposed to evaluate at 4, 3. So just like we would for functions of a single variable, to evaluate a function of two variables at a given point, xy, we're going to take the given values for x and y and substitute them into the rule which defines our function. In this case, square root of 4 plus 3. So root 4 is, of course, 2 plus 3. So the value of our function at this point would be 5. Now in part B, we have the function f of xy, which is defined as 2x minus 3y plus log of x times y, and we're asked to evaluate at 1, 1. So the value of this function at 1, 1 is given by 2 times 1 minus 3 times y, which was 1, plus the natural log of x times y, which would be 1. So we're left with 2 minus 3 plus log of 1, which is 0. So we have a value of negative 1 for the function at that point. Now, the next thing we'll consider is determining the domain of a function of two variables. So just as we would for a function of a single variable, the domain is defined to be the set of all inputs, so that is the set of all points x, y, such that our function would give a real number as its output. So here we are asked to find the largest possible domain and the corresponding range, that is the set of outputs of our function, for the given functions. So in part A, we have the function f of xy defined as the square root of 9 minus x squared minus y squared. Now, in order for this function to be defined, we need the expression under the square root, that is 9 minus x squared minus y squared, to be non-negative, so that we have a real number as our output. So solving this inequality, or rewriting it, I could express this as 9 is greater than or equal to x squared plus y squared. So here our domain is the set D of all points in the xy plane such that this inequality holds. X squared plus y squared has to be less than or equal to 9. Now, geometrically, what this domain is describing is a set of points that lie inside of a circle of radius 3 centered at the origin. Let's try to visualize our domain here. So we were looking at the set of all points in the xy plane such that the sum of x squared and y squared is less than or equal to 9. Now, if we consider the boundary of this domain, if we consider sort of the edge of our inequality, let's say x squared plus y squared is equal to 9, well, we would have a circle centered at the origin of radius 3. That is the circle x squared plus y squared equals 9. Now, if our inequality says the sum of x squared and y squared is less than or equal to 9, that means we're considering points on all circles which have radius less than 3. So we're considering all of the points inside of this disk. So this would be our domain D, where x squared plus y squared is less than or equal to 9. Now we're asked to also determine the corresponding range for this function. So for finding the range of a function of two or more variables, I typically like to find the range of values for the innermost function and work my way outward. So most of the examples we'll consider, we're working with composite functions, like in this case, f of xy is the square root of a polynomial of x and y. So let me start by considering the range of values for the function that is under the radical. Now I have 9 minus x squared minus y squared, or I can write this as 9 minus x squared plus y squared. And for this function to be defined, we said that this expression, 9 minus x squared minus y squared, had to be non-negative so that we have a real number. And let's think about the largest value that we could have for this quantity. So if we have 9 and we're subtracting the sum of x squared and y squared, well, the smallest value that I could ever have for x squared plus y squared would be 0. So the smallest number I could be subtracting from 9 would be 0, which means the largest value I could have for this difference would be 9. Now the function that we're working with is the square root of this polynomial, 9 minus x squared minus y squared, or 9 minus the quantity, x squared plus y squared. So if I take the square root throughout this inequality, that means that the smallest value I could have for this function would be 0, and the largest value would be 3. So I can say that the range of this function is the interval from 0 to 3, including the endpoints. Now let's consider our next example. In part B, we have the function f of xy, which is defined as e to the negative x squared plus y squared. So in order for this function to be defined as a real number, we have no restrictions. Recall the domain of an exponential function would be the set of all real numbers. So I ask myself, well, are there any restrictions on x or y such that this negative x squared plus y squared would be a real number? And no, there are no restrictions. This is a polynomial, which would be defined for all values of x and y. So we can say immediately that the domain is the set D of all points in the xy plane such that x and y could be any real number. But recall that this set is denoted as R2. We can take any point in the real xy plane. So our domain is all of R2. Now to determine the range of this function, again, we see that we're working with a composite function. So let me start with the range for the innermost function and then work my way outward. So here I could say, let's consider our innermost function, x squared plus y squared. Now I know the smallest value that I could have for the sum of two squares would be 0. So the sum of x and y squared must be at least 0. And if x and y are allowed to be any real numbers, then the sum of these squares could become infinitely large. Now from this x squared plus y squared, working my way outward to get the value of our function, well, we were looking at e to the negative x squared plus y squared. So let me consider the range of values for negative x squared plus y squared. So if I multiply my inequality through by a negative 1, that's going to change the direction of these inequalities. So I would have negative x squared plus y squared is less than or equal to 0. And greater than negative infinity, or in other words, we can make this quantity as small as we want. So to get the rule for my function, we have e to the negative x squared plus y squared. So if I exponentiate throughout this inequality, I would have e to the 0, which is 1, or e raised to infinitely large negative numbers, or say like e to the negative infinity, well, we're getting smaller and smaller values approaching 0. So here we find that the range of this function would be the set of all numbers from 0 up to 1, including 1, but not including 0. So let's look at some other examples. In this next example, we're just going to be concerned with determining the domain of a function. So here we are asked to find and sketch the domain of each function. And in part A, we have the function f of xy, which is defined as the square root of y minus x squared. So as we had for our earlier example, in order for this function to be defined as a real number, the expression under the square root, that is y minus x squared, must be non-negative. So if I rewrite this inequality, maybe solving for y, I would have y has to be greater than or equal to x squared. So for part A, the domain of this function is the set D of all points in the xy plane such that this inequality holds. Y must be greater than or equal to x squared. Now, if we're asked to sketch our domain, let's think about what part of the xy plane this represents. So if we consider the boundary of our domain, which would be defined by the equation y equals to x squared, well, we would have a parabola in the xy plane whose vertex is at the origin and is opening upward. Now, if we have the inequality y is greater than or equal to x squared, we're considering all of the points in the xy plane which would lie above this parabola, where y is defined to be greater than x squared. So we're looking at the set of all points above this parabola, and that would be our domain D. Now in part B, we have the function f of xy is the square root of x squared plus y squared minus 1, plus the natural log of 4 minus x squared minus y squared. So let's start by finding our domain. So for this function to be defined as a real number, first off, the expression under the radical, x squared plus y squared minus 1, has to be non-negative. And in order for this logarithmic function to be defined, its input, that is 4 minus x squared minus y squared, must be positive. Recall that we can only define the logarithm of a positive number. So solving both of these inequalities, I would have from the first inequality, x squared plus y squared has to be greater than or equal to 1. And solving the second inequality, I would have 4 has to be greater than x squared plus y squared. So notice that we have from our two conditions restrictions on the sum of x squared plus y squared. It has to be at least 1 and can be no greater than 4. So combining these two conditions, we would say that the domain is the set D of all points in the xy plane such that the sum of x squared and y squared is at least 1, but is strictly less than 4. So this would be the domain of our function. And let's try to sketch our domain. So in the xy plane, we're considering all of the points such that x squared plus y squared is greater than or equal to 1. So for the boundary of our domain, we could consider the equation x squared plus y squared is equal to 1, which would define a circle in the xy plane centered at the origin of radius 1. Now, considering the other boundary of our domain, or the other edge of our inequality here, we had x squared plus y squared has to be strictly less than 4. Now, if x squared plus y squared was equal to 4, we would have a circle in the xy plane of radius 2 centered at the origin. And here I'm using a dotted line to sketch my curve. The reason I'm using a dotted line is to indicate that this was a strict inequality. So I can't take points on this circle since the inequality was strict, so I'll indicate that by using a dotted line and a solid line for that inner circle, since I could take points on that circle, since it was not a strict inequality. So what we're considering here is the set of all points that would lie between these two circles. So we have a sort of ring shape for our domain D. This is actually something called an annulus. It's the region between two circles. So let's look at some other ones. In part C, we have the function f of xy, defined by the square root of x plus root y, plus the square root of x squared plus y squared minus 16. So in order for this function to be defined, the expressions that we have under each of these square root terms must be non-negative. So for the square root of x to be defined as a real number, we need x to be non-negative. For root y to be defined, we need y to be non-negative. And for the last radical expression in our function to be defined, we need the quantity x squared plus y squared minus 16 to be non-negative. Or solving this last inequality, we would have x squared plus y squared has to be greater than or equal to 16. So here, the domain would be the set of all points D in the xy plane, such that these three inequalities hold. That is, x must be non-negative, y must be non-negative, and the sum of x squared and y squared has to be at least 16. Now, to visualize our domain for this function, let's consider what part of the xy plane that we're working in. So we're told from our domain that x and y must both be non-negative. So we're only considering points in the first quadrant of the xy plane, where x and y are both at least 0. And then our last inequality defining the domain was the sum of x squared and y squared must be at least 16. Now, if we consider the boundary of this domain, or the boundary of that inequality, we would have the equation x squared plus y squared equals 16, which would define a circle in the xy plane centered at the origin of radius 4. And I would use a solid line to denote that circle here. Since this was not a strict inequality, I could consider points on this circle. Now, if the sum of x squared plus y squared must be greater than or equal to 16, that means that we would be considering points that lie on circles of at least radius 4. So we're considering points that lie outside of that circle, still in the first quadrant, since x and y had to be non-negative. And since in our first two inequalities we did not have strict inequalities, that means that we could consider points on the x or y axis as long as the values of x and y were at least 4. And so this would be a sketch of our region D for the domain of this function. So let's look at one other example. In part D, we have f of xy is the square root of 9 minus x squared minus y squared, all over 2x plus y. So first of all, in order for this function to be defined as a real number, we need the quantity under the square root, 9 minus x squared minus y squared, to be non-negative. And since we have a function which involves a quotient, we have to be careful that we do not have division by 0. So we need our denominator, 2x plus y, to be a non-zero quantity. So let's see what we would have for our domain. If we solve this first inequality, I would have 9 has to be greater than or equal to x squared plus y squared. And solving this non-equation, or this inequality on the for the second part of our domain, I could say that y cannot be equal to negative 2x. So for this function, the domain is the set D of all points in the xy plane such that these two conditions hold, namely x squared plus y squared has to be less than or equal to 9, and y cannot be equal to negative 2x. So let's try to visualize this. So in the xy plane, we're considering all points such that the sum of x squared and y squared is less than or equal to 9. Now, if x squared plus y squared were equal to 9, we would be describing a circle centered at the origin of radius 3. So this would be the boundary of our domain, and we're looking at the set of all points where the sum of x and y squared is less than or equal to 9. So we're considering points that lie on circles of radius less than 3. So every point inside of this circle. However, we also had some restriction that y could not be equal to negative 2x. Now, the equation y equals negative 2x would be describing a line through the origin of slope negative 2. And I am saying that y cannot be equal to negative 2x. So we would be considering all of the points that lie inside of this disk except for points on this line.